In the same way that the space age is now getting decidedly long in the tooth, the atomic age will, in just over a decade, be celebrating its 100th birthday. The discovery of the properties of radiation, along with the discovery of the inimical effects of radiation as researchers and factory workers alike began to die from it, unlocked an entire branch of physics that had hitherto not even been speculated on by the collective sciences of the Earth. What this offered was a practical realization of mass-energy equivalence, whereby energy and mass, rather than being two entirely separate things, were in fact discovered to be the same thing, realized in two different ways. However, this equivalence was found to be far less than even, with the annihilation of a fraction of an infinitesimally insignificant amount of mass yielding more energy than could reasonably ever be consumed. The only difficulty being that mass is really rather exceptionally hard to annihilate, no matter how hard you hit it. Some heavy radioactive elements offer a solution to this problem. When struck by certain subatomic particles, they are unstable enough to split into two smaller elements, releasing some of their mass as thermal energy when they do, in addition to releasing further particles that split further atoms. This fission of the atom is why the device in which this is done is referred to as a fission reactor, which sounds a great deal more impressive than an atom pull-apart-gets-hot machine. A particular property to note in the design of a fission reactor is what is referred to as the multiplication factor. This is the proportion at which splitting atoms split other atoms, and it must be very carefully controlled. Anything less than 1 is referred to as a subcritical state, as each splitting atom splits less than one atom until the whole thing sputters out and you don't have a reaction anymore. Anything more than 1 is referred to as a supercritical state, with each split yielding more than one split until you also don't have a reaction anymore, but in a much more dramatic way. A value of 1 is referred to as critical, in which each splitting atom splits one more atom. If a nuclear engineer ever shouts, "It's about to go critical," this does not in fact mean that the reactor is about to explode, but rather that it is about to start working exactly as intended. The way that this is controlled is through the use of a moderator. The moderator is a material that carefully controls the number of particles that are travelling at exactly the right speed to allow reactions to happen. Not too slow, not too fast. The speed that Goldilocks would break and enter for. The majority of reactors use water as a moderator. If the water boils off, the moderator is lost, and no further reactions can take place. However, other reactors use other means of moderation. In the case of some reactors, loss of water can increase rather than reduce reaction. Most nuclear engineers agreed that the first type was better, until the 26th of April 1986, when very suddenly all nuclear engineers agreed that the first type was better. However, other issues with all nuclear reactors of any design include the exceptionally high upfront cost, and the question of what to do with the spent fuel rods, which contain up to 98% highly radioactive unused fuel at the point where the accumulated waste products make reaction impossible. Proposals have been made for reprocessing, however this adds a continuous cost on top of the exceptionally high upfront cost, with most nations opting to follow the three-step plan of 1. Dig big hole, 2. Put the waste in the hole, and 3. There is no step 3. Because of this aforementioned problem, coupled with the other aforementioned problem on top of the third aforementioned problem, from the mid-80s onwards, many nations opted to return to the use of coal to generate electricity, thus solving the problem forever.